Okay, let's start learning deep neural networks. Actually, let me show the content, the little see maybe. Intro to deep neural networks and losses and activation functions, regularization, optimization, and metrics coming. We have first part, second part together, and launch at 1 p.m., and then activation functions, regularization, and then having a 10-minute break, and then optimization. We may have a break like 10 minutes, and then part 6, metrics for evaluation and closing. Probably like 4:40 it's going to finish, I think. For the first part, it's really kind of intro, very short parts. Especially in part 2, especially Dimitri will show some implementations. Yeah, it's going to take like around 1 hour for implementation until the launch. Okay, let's start from the part 1. Very shortly, just I want to summarize the learning concept here. In machine learning, you know that we just try to learn a function. That function is just maps an input to an output. So the main aim is just find an optimum function. So you know that there are many types of functions we all know from like our childhood, like in the middle school or high school. We just learn about functions, how to draw them, how to like analyze them. For example, like taking the first derivative of a function, we get like slopes. Taking the second derivative, we get the local minimum and maximum points. These are important concepts because, especially in gradient descent and backpropagation in neural network, we just all talk about these gradients, these slopes, the first derivative and second derivative. So this is actually, we in machine learning, because the neural network is also part of machine learning, we just try to find an optimum model or optimum function that separates data or classify data. The map the input variables into like output. So in machine learning, there are many algorithms. They are differently treating the data, and they are differently like approximating a function. For example, linear regression, just predicting. I'm just trying to find a function to feed the input values and predict some output values. This is just predicting values actually. But in logistic regression, it's just trying to find an optimum function just for separating or discriminating values or data. So we have a boundary and then they separate the data and then give like outputs like labels. SVM is also very similar to logistic regression, and then but the difference is we still have a decision boundary, but we have also two support boundaries or two support vectors to treat both of sides, both of the data fairly. In case of ensemble modeling, they just combine the different model outputs and then average them to get a better approximation. And like k-means, it's just like clustering the data into like depending on the number of clusters. In decision tree, it's a little different actually. There are just yes or no questions, kind of. In random forest, it's the combination of decision trees. It's also kind of ensemble modeling, just averaging these different decision trees outputs. When it comes to neural networks, which is our main focus here, we can get a more generalized solution or more complex functions we can find. Because by adding the extra neurons or layers, we just also it means that we add extra non-linearities, which is very important for generalizing more complex data sets. So we focus on these neural networks throughout this workshop. So actually, this is our task is just fitting the optimum function to our data set or our problem. Not maybe data set because it's not true definition. Maybe the problem because whatever we have in our hand, it should work when we grab any of these algorithms. Basically, what we do in all the machine learning family, we just get the data and then featureize them like spam or non-spam, and get the feature vectors, and then select a model and select a method and then train and then get our best model or get approximate the best function, which is classifying or separating data. And then evaluate that, and then just changing parameters, we try to find the best, maybe optimum function, best function, we can tell. So in brain, it's quite interesting. We have like neurons, because from here we just start like neural networks. In brain, we have hundreds of millions of neurons, and each neuron are very densely connected to each other. As you see here, like there are dendrites, which is just receiving the signals or input from the other neuron, and then processing here, just like doing some like summation or doing something. Just combining these signals, and then by using through the axons, which is transferring these signals to the another neuron, but there is still a connection here, like synapses. So here is I think interesting because it's like a chemical operation is happening there to transmit the data. This is in neural networks. This is I think interesting. Because when we model, we get this, when we formalize this neuron, just a simple neuron, we just get, we get dendrites as input points, receiving signals, and then just combining them here, like summing all these signals, and then adding an activation, like an axon, and transferring this data, firing all this signal to another neuron. So this is the basic idea behind the neural networks. When we look at directly, in a mathematical way, what we have in neural networks, we have a feed-forward operation and we have a backward operation. We also have an interim operation, which is in feed-forward part. We just receive the data, receive the signals or input variables, and then apply some weights, and then sum them, and apply an activation function, and then get a prediction or an output. So we use this prediction because with our this is prediction. This is our true result. We expect these actually, and then basically subtracting them, which is very basic calculation of error, and then get gradients. Calculate the gradients, and after calculating the gradients, we just apply our optimization process, to update these weights. So this is the most critical part because we all learning these weights actually. And then after getting these gradients, we just backpropagate because we need to because in feed-forward style we don't have any update yet. We all have the same weights at the end of the process, so we need to go back to the network and then update these weights by using these gradients. So this is very critical, the maybe most critical part, the gradients or the loss. And then we go back and then apply these gradients on each neuron and then update our weights and then do this process again and again until we get an optimum function or optimum, like not function, maybe the parameters. From here, like losses are starting. Why loss is important? Because we all learn from our mistakes or like experiences. And every human or human-made system needs to optimize itself. Because without any optimization, we repeat the same process again and again. So there is no meaning for that. But to optimize something, we are going to need like an experience or a quantity, especially in case of like algorithms. For human, experience maybe. We experience something, we do some mistakes, and then we optimize our mistakes. We, try not to do again the same mistake. This is the optimization problem. There's a quick way to just do something like this, in a very quick way, but there's a wise way. We can compare our expected and observed values. What we expect, a dog, what we get, like a cat. So let's compare our error, expected versus observed. So use these laws in further processes. Loss concept is very close to distance metric analogy. What's the distance metric? It's just basically we just try to find how our model is how our predictions are getting close to the true predictions or true values. As you see here, we have a network like neurons, and then we got predictions, different predictions, like 3 predictions, but we have true values 0, 0, 1. So there is something missing. So we just compare these predictions and our true values and get, calculate our error and use this error for optimization problem, for the optimization process. And the next, we can do actually this comparison, this comparing operation, like basically like checking in a visual way, but it's not logical, because visually checking is really difficult and we can make mistakes. So we need some quantitative ways to check the observed and the expected difference between the observed and expected values or distributions. In machine learning especially, if we, let's say we have an input and we have a feature extraction part, or like we can add also use like pre-processing step, cleaning the data. This part is the most important part, and then the second important part is just measuring the distance. How our predicted values differ from the expected values. So we need to use some mathematical approach to get this difference. Some important concepts, classification and regression, because this is important, I think. Classification is just predicting discrete values, predicting labels actually. It's spam or not, it's 0 or not, for example. Regression is like predicting continuous values, just predicting values actually. It's very simply, this is the regression, this is the classification. Why? Because we will group our loss functions into regression and classification. Mostly, in regression problems, these common actual losses like L1 loss, L2 loss. There are many other losses, but these are very basic losses. just very basically, you see subtracting the true values to predicted values and taking an absolute and summing all these all different predictions and then averaging them. In L2, we have a square, no absolute approach, as we are squaring this difference. In classification, we mostly use cross entropy. It's also called like log loss because we are taking the log of our predictions. And there is a hinge loss also. It's very common, especially using SVMs in support vector machines. If you compare, for example, if speed is important for you, maybe you can use hinge loss. If accuracy is important for you, you should use the cross entropy. It's going to give you like more accurate results. There are many losses depending on the application, depending on the problem. But I think not so commonly used, especially in deep learning. We mostly use the cross entropy and the different types of cross entropy. And MSE, in some applications, especially like in some like generative adversarial network, we use sometimes L2 loss, L1 loss. These are many losses. Actually, we can try for depending on our application, we can try all these losses. But mostly in machine learning, other machine learning applications, we may benefit from these losses. Okay, let's look at the deep network, how things happening. This is also like a reminding graph. We have an input image. We extract all features using convolution operations and pull them, and then get still the feature maps, and then we feed these feature maps after flattening to like dense layers. And we get an output, which is like dog, cat, like predictions. But our expected predictions are 1 to 0. This looks actually right. This is predicting, this is dog, yeah, it's okay, this is dog, but there is still a little confidence problem. Not problem actually, this is 0.9 to 5 is very high, very confident result, so it's good enough for us. But yeah, we still should compare these two outputs, 0 to 0.05 and 1 to 0.95 to get to calculate the loss. Let's say this is cross entropy. But I want to show you actually here because we have also an implementation on this. Let's say we have a neural network, two neural network process, but let me talk on this. We have like one true prediction, another true prediction, one false prediction. We have one false prediction, two true prediction. If we just basically count the loss by hand, like me, we get the loss 1 over 3 because we had the one wrong prediction, false prediction, and our total predictions is 3 because 1 to 3 we have 3 predictions. So our loss is like 0.33. If we use mean square, we get maybe more accurate result because this is not so accurate because we are counting by hand. I think this number is wrong. So I didn't change. And then if you use the cross entropy, we still get a different result, maybe more accurate. Dimitri has an implementation on this. We talk about therapy. There is another interesting loss concept, which is again, if you attended GAN workshops before, maybe you remember. This is really starting a new era, I think, because normally, so far we had these losses, these L1, L2 cross entropy. There are many types of losses depending on the application, regression, classification, or segmentation, or any application. We choose one of these losses. But GAN just propose another interesting, maybe most interesting approach. It's just an implicit loss. What that means, it's not actually using these losses, it's just learning its loss itself. How it's learning, this actually in GAN setting, we have a generator neural network, this is the discriminator neural network, and data, real data is coming here, and noise just coming here, and this discriminator comparing whether this noisy input is real or not. But how it learns, it just learns through this discriminator network, because discriminator network behaves like a loss function. Because these generators just try to generate very real looking samples or images, for example, and discriminator just check these whether this is like real sample or not, and then give a feedback to generator. So it's actually its loss is discriminator loss, being discriminator loss. So this process is a very balanced process. By this balance, actually, this GAN setting is just learning its loss itself. What is the meaning of this? Normally, depending on the problem, depending on what you have, for example, you are working on an object detection problem or a segmentation problem or I don't know, any NLP problem, you should choose your loss. You should choose your maybe the best loss. Commonly, people use like cross entropy for mostly in computer vision world. But sometimes, especially these research papers, are little biased actually, because they are using all the similar data sets, all the common data sets. When you use your own data set, your like real world data set, any problem you are working on, the algorithms may fail. So there are many reasons behind that. Sometimes laws, sometimes parameters, sometimes your architecture. But actually, what GAN does, GAN is just a kind of a generalized solution for any problem. You can apply GAN on any computer vision problem. Recently, people just publishing very interesting research actually. For example, in computer vision, anomaly detection is normally people work on anomaly detection problems using the common computer vision algorithms. But recently, a paper just published, and then they tell, okay, we can use GAN even for anomaly detection, for segmentation, for any classification problem, because it's learning its loss itself. Yeah, this is, I think, very important. If you have a problem with loss, you can use GAN for your application, but yeah, for now, not so stable. Maybe in a couple of years, or maybe in 5-10 years, we may see GAN is replaced with these losses. Not replaced actually, because it's very difficult to, yeah, it's time-taking process. There may still many things to do on GAN. Okay, what about designing a custom loss? Like GAN also is a kind of custom loss. Someone just invented it, designed it. So depending on the problem, we can design our loss again. For example, this focal loss is a very good example, I think. This is applied on an object detection problem. Normally in object detection algorithms, there is a problem of like there is object or not. If there is, yeah, this objectness, because of this objectness problem, the result is always, I mean, the accuracy is very low. You are getting the very low accuracy. So what they did, they just very simply, this is the classical cross entropy laws. They just thought, okay, let's add something extra here, like focal parameter. And then they got the very, the promising result. So this is now usually normally in one. Now I think these networks, retina, it's called like retina network. It's now is the best, I think best object detection algorithm because of these newly introduced laws, focal laws. So it's very important to sometimes introduce your own laws depending on your problem. We can't simply rely on all these simple, the common losses. For common problems, yes, it's okay. But for special cases, we should maybe consider extra constraint, like extra loss term. Okay, so there is an interactive implementation here. We have Dimitri. Dimitri is going to implement the basic losses and show their differences. And then a custom loss function is going to implement